Hi. So thanks for inviting me. So I'll be talking about proving some things in computational complexity using stochastic calculus techniques. Right. So in this talk, I'll be focusing on this problem called the Forrelation problem, and eventually I'll tell you various properties about it. So first, let me define the problem. So I have x in plus minus 1 to the n be a uniformly random Boolean vector. In this talk, I'll use Boolean to mostly mean plus minus 1, although sometimes I'll also switch to the more conventional 0, 1 bit strings. So the problem is to distinguish between these two distributions. So firstly, I draw y from plus minus 1 to the n, also independent from x and uniformly random. And the second distribution is that I take y from plus minus 1 to the n such that y is equal to the sign of the Hadamard transform of x. So Hn is just some change of basis matrix, which I'll define right now. So the Hadamard matrix, it has this recursive definition. For this talk, it's not actually super relevant what this definition is. You just have to remember that all of the entries are bounded by 1 over square root of the dimension of the matrix, and also it's just some change of basis matrix. And I guess the importance of this thing is that it's the Hadamard matrix is sort of related to the Fourier transform of like the bits. So I guess that's where this thing comes from, and it's also like very important in quantum computation. Okay, so back to this problem. My second distribution is that y is kind of like the Fourier transform of x, but then I round it to plus minus 1. And I'm looking for an algorithm which, when it's fed x and y, with high probability, m will output the correct answer of whether x and y came from distribution A or came from distribution B. So this probability is like over the probability of the random bits. And in some, I can also consider cases where this m is probabilistic. So this probability is also over the randomness of the algorithm. That's one thing I want to point out right now is like in this talk, I often will just confuse, I'll just use the same like description for functions and algorithms. So whenever I talk about functions, I'm often just thinking about the function as representing an algorithm, like bringing the input of an algorithm to the output of an algorithm. I think that's a very common thing that people do in computer science, but I guess not so much in math. So this problem is called the Forrelation problem, and it was first formalized by Arison and Bennis in 2015. All right,
sorry, just one question. I think I didn't get it. Like the x is also in the input of the algorithm, right?
Yeah.
So you observe x, but then you say you average over all possible x's.
Right.
I see. And so you're interested in the probability is over y and x together with the randomness in the algorithm, possibly.
Yeah.
Okay.
Yeah. Okay, so yeah, it more or less suffices to just show that basically like if I take the expectation over the distribution A and I take the expectation over the distribution B, then M sort of outputs a different number in expectation. So okay, I guess this two-thirds thing is also not very important. Like we just really want it to be like some constant strictly greater than half. And so eventually we'll go on and like work out what all the constants should be. But right now I'm just saying that it should be like some strictly bigger than 0 constant that doesn't depend on, that's like, okay, it depends on n in a good way. So I guess at this point you might be like, hey, this problem isn't actually very hard because like one very simple distinguisher is just you compute the inner product of x and y, and you output this. You output this inner product that's x with hn of y, and and then you say that okay, it came from distribution A if this inner product was low, and it came from distribution B if this inner product was high, and like you'll be correct like most of the time. So yeah, this test even has the benefit of being a low degree polynomial because the inner product, if you expand it, it's just degree 2 polynomial in the bits of x and y. But I guess so the thing here is just that we're looking for something in the complexity world of like, we're looking for something that's even more restrictive than just being algebraically simple, like a low degree polynomial, because essentially we want it to be computable in like a very restrictive model of circuits called these like constant depth circuits. And it turns out that this particular polynomial is not computable by a constant depth circuit. So okay, let me tell you about what I'm going to talk about throughout this talk. So our goal here is to show that this correlation problem, it's hard for some models of classical computation, but it's easy for other models of quantum computation. And this problem and its variants have been studied by a lot of people in a series of papers. And I'll mostly be presenting results that came from this paper by Raz and Raz-Tal in 2019. Although I'll be going through the proof in a slightly different and hopefully more simple way. So the key idea behind this approach is this like kind of wacky way to generate random bits. So you might think that like -1 and +1s are like very simple, but somehow if you make a change in perspective, instead of viewing them as just ±1, you reformulate this problem as over the real numbers, then that like gains some more control over what the distribution is. And then step 2 of the solution is you make another change in perspective, and you think that, okay, these bits, they're not just going to come from a real distribution rounded into ±1, but we're going to generate the bits using a stochastic process. So yeah, I'll go into a lot more detail about all of this stuff later. But first, let me just tell you a story about complexity classes. So I guess I'm not going to go into a lot of precise technical details here. Everything I say here, it can be made precise, but you should just, I guess, take it as some intuition. So okay, I'll draw some pictures about complexity classes. So first, there's this class of functions that are computable by polynomial time machines. So we sort of think of like this class is called P. We sort of think of them as the problems that can be solved by a physical classical computer in a reasonable amount of time. And then containing this class, there's another class of functions called NP, which I guess surprisingly doesn't actually stand for not polynomial. It stands for non-deterministic polynomial, which just means that the solutions to these problems are checkable in a polynomial amount of time. And complexity theorists generally believe that P does not equal to NP, but we don't actually know how to prove it. So I guess what that sort of means is that we believe that there are problems that are not solvable by a physical classical computer in a reasonable amount of time. And once we've gotten here, we can sort of keep going and keep building more levels of non-determinism in to build these like complexity classes. They are mysteriously called pi2 and sigma 3 and so forth. And then when you take this to like sort of its limit, you end up with the class of functions that's called the polynomial hierarchy. So this is like kind of, if you gave classical computers a lot more power, these are the problems that they can solve. And then inside this entire picture, I will insert another circle, which is like the class of functions that is solvable by a quantum computer in polynomial time. And we sort of think that this circle, like it lies here, it should contain some function, some problems that a classical computer can solve, but it doesn't contain like everything. So I guess one property of working on complexity theory problems is that we don't actually know for sure that any of the containments here are strict, and we also don't know how to prove anything. So instead of saying that I will prove definitively that the class VQP and the class PH are different, I'm just going to give some complexity theoretic evidence that they are different, which is to say I'm going to prove something that's like a similar flavor of problem, but I'm not going to actually prove the statement that I want. Okay, so let's zoom in on just these three classes of BQP, PH, and BQP, MP, and P. So back in 06, Bennett, Bernstein, Brassard, and Vazirani, they showed that they gave some evidence that BQP is not contained in MP. So they, in fact, somehow showed a statement that could sort of imply that like the MP complete problems, which are the problems we think are in MP but not in P, they are also not in BQP. So they are also not solvable by a quantum computer. And then until recently, we had no real evidence of the reverse. So it's like, it could have been that BQP is like contained in MP. So, but this paper by Aronson and Baines, it sort of conjectured that the Forrelation problem is exactly the problem that is going to lie in BQP but not MP. And sort of this is like not exactly, yeah, sort of this is not surprising just because, you know, the quantum is supposed to be really good at doing the Fourier transform like for free. And okay, so recently in this paper by Ranras and Avishai Tao, they showed like in the same sense of complexity theoretic evidence, they showed that they gave some evidence that pH is not contained in BQP. So this Forrelation problem, it not only like separates MP from BQP, but like it separates this huge class of problems that like it's like classical computation plus plus, like even that class cannot solve this Forrelation problem. So yeah, this is, I guess this is the result I'll mostly be talking about with like this reformulated proof of using the stochastic calculus techniques. Okay, so yeah, I guess are there any questions so far?
Sorry, so you said there was an additional restriction on like I forget what it was. It was something depth circuit.
Right. So yeah, the restriction on the problem is going to be that like it's computable by a low depth circuit. I guess I'm just about to go into what that's about and the definitions and so
Okay,
on.
okay, and that's this is all this stuff is assuming you're working in that setup, not
Yeah.
okay, cool.
Yeah. So okay, I guess like I'm gonna tie in what I said. So like all these nice circles, I'm gonna tie that in with circuits. So I guess I'm gonna give you this definition of MP, which is not like really the definition you'll see at first glance, but one way of thinking about MP is you have this function that takes in like n-bit input and it outputs 0 or 1. So one way to think about it is you're given 2 to the n possible inputs, and you just want to know if any of them will cause the function to output a 1. So you can sort of think of MP as it's a giant like OR gate over all the possible inputs, and if any of them cause your function to be 1, it will output a 1. And then you can add like more layers to this definition by saying, okay, so instead of just saying I want to compute functions that are going from they are like 0, 1 to the n to 0, 1, I have like 2 inputs now. And so the first input, I will I'll have like 2 to the n possible values of x, and I'll have 2 to the n possible values of y. And then I'll put like this giant OR gate over all of the 2 to the n possible values of x, but it's also associated with 2 to the n possible values of y. And so I just keep going like this, and I have like 2 to the n x's and 2 to the n ORs. And then I put, okay, wait, oh, and then I put a giant AND gate on top. And so what this sort of means is that I want to, I will output a 1 if any x and all y's cause the function to output a 1. So yeah, so this is like, and then when you keep going with like a constant number of layers like this is like basically the definition of the polynomial hierarchy. And in some regards, this is like exactly the same thing as a constant depth circuit, which is I have n input gates which are valued 0 or 1, and then after that I can have some AND gates where each gate has a polynomial number of inputs, and then it feeds into another layer of OR gates where each gate has a polynomial number of inputs. And then finally, I have like some, like I do this for like a constant number of layers, and then I output a 0 or 1 at the end. And yeah, so I guess this like, the similarity is not just sort of pictorially, it's like it can be made precise.
Just wondering, a very kind of stupid guess is, looking back to this Forrelation problem, the reason why you cannot model it with a constant depth circuit is because Hadamard has logarithmic number of recursions to compute and not constant one. Like when
yes,
when I compute the Hadamard transform, I mean, I was confused, as probably other non-specialists here, by the fact that Hadamard is pretty easy to compute, right? I can do fast Hadamard transform in the log time and log n, where n is for each layer. But probably the problem is that I have log kind of, my depth grows with the dimension of the problem, right? Which it shouldn't.
Yes, yeah. So I guess it's essentially kind of saying that you're only allowed to do like a constant number of transforms rather than logarithmic. Yeah, so somehow I guess what's going on is that like, yeah, okay, maybe, yeah, no, I think that's, sorry, that just, I thought of something, but it would just be more confusing. Yeah, so I guess what's going on is like the constant depth circuits are like actually like a super restrictive class. And there's some way to make it so that these, like what's computable by the constant gate circuit, the constant depth circuits is like the same things that are computable by the polynomial hierarchy given like an access to an oracle. And that's like the model that we're going after. So yeah, so I guess the sort of the analogy that like, okay, I don't, wait, did someone else have a question also? Okay, yeah, so I guess like that, it's just that MP is like sort of similar to a depth 1 circuit, and then you sort of think that, okay, if I'm thinking about a Hadamard matrix, then it's certainly not like it's, you're tensoring like log n items, so it's like sort of too complex. And then what's sort of going on is that like I sort of need to say that I also cannot do it with just a constant number of queries. So yeah, like doing this sort of, I'm going to prove it for this small model of like this big complexity class is like kind of what complexity theorists refer to as like complexity theoretic evidence. And it's like, I guess it's considered a good result when you're able to prove statements of this kind of thing, of this kind of form. So yeah, I guess after doing all of these funny reductions, I will eventually just want to say that one query quantum algorithm, it will be able to solve the Forrelation problem, but a constant depth classical circuit will not be able to. Okay, so let me say some things about constant depth circuits. So they compute this function going from 0, 1 to the n to 0, 1, and it's a multilinear polynomial of degree at most d, and it's not very powerful. Like we know many examples of problems that are not computable in this model, and in fact, like I think this is like one of the only models that we are able to prove like unconditional lower bounds against. Okay, so I guess what I've said so far is basically just like motivation for really solving this problem. And now I'm going to try and get into the math. So, well, okay, so I'm going to talk a bit about just Boolean functions. I guess we usually think about Boolean functions as being from 0, 1 to the n to 0, 1. And then the first step when you want to do like anything analytic with a Boolean function is to map the 0, 1 to +1 and -1. Yeah, and this is just so that like this funny thing happens where if you like square any one wait. Sorry, I think that, okay, I typoed that, but like basically your input, if you square any one of the input bits, it gives you 1. And so that means that all Boolean functions are multilinear, kind of in the sense that it can be expressed by this, it can be expressed by a polynomial where every power is 1, like every power of a different input in the term. So yeah, and then I kind of write this notation as just f of x is equal to some sum over some coefficients times the terms. And so C of s is the coefficient associated to the term x sub s, which is like for each subset of n, there is a term in the polynomial. Yeah, so I think sometimes people talk about this as the Fourier transform of the function, but I guess I just didn't want to get into all of that terminology today. Yeah, so yeah, hopefully that makes sense. So, okay, and then I guess the next like sort of very like classical move is to, okay, I take this function that goes from -1, 1 to -1, 1, and then I interpolate between the range points. So for each x, I just basically set it to be f of 1 with half plus x, and then I set it to f of -1 with 1 minus x over 2. And so now now I can think of f as being from R to R, and it's now a linear function. So this also applies to like the n-dimensional case, and that's how I go from thinking about f as being over like -1, 1 to the n to being from the reals to the reals. But then it's like a super simple function with like a lot of structure over it. So, okay, like this sort of interpolation thing, it can also be reversed. So if I have some multilinear polynomial that goes from -1, 1 to the n to R, and like some distribution that I want to feed into the multilinear polynomial, I can do a rounding trick that says, okay, so if I actually wanted my distribution to be from like bit strings, then I can just sample something from my original distribution and do this rounding step where for each coordinate I take the zi and then I set it to +1 with some probability and -1 with some probability. And then it's true that if f is like of sufficiently low degree, then if you just do some like, if you just apply some concentration results, it will be the case that the expectation under the real distribution and the rounded distribution are approximately equal. So I guess this is just to say that like after this, I will not be worrying too much about the range of the function, and I'll just be sort of thinking about them as real functions. So yeah, so I guess now the thing to do is to like, it's like we have like sort of shifted our perspective from thinking about the input distribution as a bit string to being distributed on Rn. And so I'm going to rewrite the correlation problem in this like Gaussian way, which says that okay, so now instead of drawing x and y from plus minus 1 to the n, I'm going to let them be Gaussians from n-dimensional Gaussians centered at 0 with covariance epsilon times the identity matrix. And I want to distinguish between the cases where x and y are independent and where the covariance of x and y is equal to the Hadamard matrix. So, okay, yeah, I guess I also said earlier that, you know, there's something about how your distribution should be contained within this -1 to half, the -1/2 to half block. But yeah, we can, if you set epsilon appropriately, then you can do some truncation stuff to make it all work out. So, okay, so this is like sort of the Gaussian form of correlation. And then now the problem is just to say that I want to show that there's one query like quantum algorithm such that this the expectations under distributions A and B are like more than some constant, and but for any function that's computable by a constant depth circuit, the expectations are like smaller by some, I don't know, like let's say a quarter times the same constant or something. And then this will be enough to say that, well, this is like this problem is a hard example that separates the power of quantum computation from like classical computation. All right, so do I have questions here? Okay, great. I guess moving on, so okay, I'm going to talk about how to prove the main result. I guess I'm not actually going to get into like too much detail about what the quantum algorithm is all about. It's just basically there's like a gate in quantum circuits called the Hadamard gate, and if you just apply that gate, it like sort of automatically gives you the result that's this in the product thing that we earlier talked about. And also this is, yeah, so the paper of Aronson and Abanes showed that this is like a one query quantum computation. And then you can do all of the stuff I said about you do the rounding, the distribution, and the truncation and whatever, and it all works out. So, okay, instead we're just going to talk about the classical lower bound, because that's like sort of the more interesting part of this puzzle. Our next, like, so, okay, yeah, so we want to show that like a low degree circuit can't distinguish these two Gaussians. So our next move is actually like to do this, like, I guess I don't know if it's strange, but it's I don't know if it's strange to you, but it was definitely very strange to me to say that, well, okay, I'm going to imagine that this truncated Gaussian is generated by a stopped Brownian motion. And so yeah, so like I guess this in one shot it sort of takes care of both the truncation part and like the Gaussian part. And yeah, and then so I want to then just apply Ito's lemma to this. So I need to say some stuff about the second derivatives of any low degree, low depth circuits. So I guess the main sort of technical theorem here is just saying that, okay, if I have some function that's a multilinear polynomial computable by a constant depth circuit, then I take these two distributions as, so D1 is just a uniform distribution on plus minus 1, and then D2 is like an n-dimensional, it's like an n-dimensional stochastic process with diffusion matrix that's equal to this HNI matrix, and it's stopped at the minimum of epsilon and the first exit time of this minus a half to the 2n block. Then I will say that the difference in expectation under these two distributions, it's going to be bounded by epsilon times some polylogarithmic factor over square root n. So yeah, I guess I would say that the square root n factor comes from the fact that the HNs are normalized so that the entries of HN are all less than square root n. And the polylog n factor is going to come from bounds on the second derivatives of f. Okay, so yeah, let's think about what the derivatives are of multilinear polynomials. So if I have some function f that's a multilinear polynomial, it's expressed in this form of, for every subset of n, I have some term and some coefficient. Then if I take a derivative of it, it just means that I will only keep the terms that have the I inside the term. And okay, I guess, wait, sorry, that should be xs set minus I guess. So because you did a derivative of the polynomial. But the main point is that if you then substitute in 0, the derivative of f at 0 is exactly equal to the coefficient of the term. And yeah, so okay, then I need some other like analytical lemmas about these functions. So first I'll observe that all of the second derivatives of f are just equal to 0 because they are multilinear. So if you hit it with a derivative, with like the ith derivative twice, it will just become 0. And then I guess I will also find out that if this because okay, I guess from this previous slide, what I wanted to do is to control the derivatives of f at 0 in terms of the coefficients of f, and I can also do something to show that if the derivatives at 0 are less than some constant, then for any x within like some bound, the derivative of f there is also going to be less than some constant. Okay, and then one thing that recently got proven is that this bound on the sort of second, all the degree 2 coefficients of f. It's like this argument is actually pretty involved, which is why I won't get into it, but it says that if you look at all the degree 2 coefficients of a constant depth circuit, that's going to be bounded by a polylogarithmic factor times n. And okay, so I guess what this sort of builds to is saying that if I have a multilinear polynomial and I look at some region near 0, then I can bound the derivatives of the function there by just something times the second degree coefficient, the second level coefficients, which are bounded by this other theorem that I'm going to not get into.
Just like
Okay.
a very, can I ask a very simple question? Maybe in the interest of time.
Sure.
So I just trying to understand. So you have a multilinear form, right? Where where all the variables are in power. In every monomial, the variable is with power 1 or 0.
Yeah.
So I take the derivative and then I substitute 0 for all the coordinates.
Oh, it's not. Wait, what do you mean by, sir?
The sum of the products, and each product is a constant times a bunch of xi's, where any xi is at most once.
Right.
Okay. So when I take the derivative in xi, there are either the terms, some of the terms they did not contain xi to begin with, so they will be zeros.
Yeah.
The other ones did, and so this one will be 1. So the derivative in, okay. It will,
right.
Okay.
And then if you substitute in 0 for the x, then the only term that remains is like the constant term associated with your xi.
So it was a term like that, right?
Sorry, what?
Ci, okay. So to begin with the word, okay, I see.
Yeah, so to begin
Ci
with,
is a notation.
Ci is the,
I get it.
Ci
Yeah,
is
now
that,
I get it.
Yeah, sorry. This notation
Maybe you told it. Maybe you told it. Maybe I just missed it. Okay, now I get it. Thanks.
No, it's good. Thanks. Yeah, thanks for the question. Yeah. So okay, I guess this is also true if instead of having this like delta I here, I wrote like delta ij of like f of 0, it's going to be equal to c of like ij. So it's like how I can obtain the coefficients of the polynomial is just differentiate the multilinear function, and then I substitute in x equals 0. Okay. Yeah. So okay, I guess now I'm just actually going to talk about how to prove the theorem, which actually just comes from this thing called Dynkin's formula, which like once you apply that, okay, so first you observe that this for the d1, which is the uniform distribution on plus minus 1 to the n, the expectation of a multilinear polynomial over d1 is just the same thing as f0, because each of the coefficients are independent. And right, so I can just use this formula with the I guess this thing is meant to be like the infinitesimal generator, and that's just equal to the diffusion constant. And so I can, okay, wait, so I just use this thing, and then sort of the proof just sort of goes like, oh, it didn't come on line by line, but that's okay. Okay, so I'll just tell you a bit about what happened here. So I guess I started off just by like plugging in the constants, and then I get that this is equal to some, you integrate over from 0 to the stopping time, and then you multiply by each of the coefficients, the coefficients inside this like covariance matrix, and then I just like sort of take the supremum over the all of the time steps, and look at this. Okay, so first, I guess from here to like the next step, I just use that tau is less than epsilon, and then I take the supremum over the integral, and then next I sort of observe that this is equal to zero when I equals to j. So what this does is sort of it says that I no longer need to look at the identity matrix part. So the only like relevant bound is the bound on the H matrices, and then I know that the H matrices are bounded by 1 over square root n. So each of the entries of the Hadamard matrix, it's like bounded by the square root of the dimension of the matrix. And so once I do that, I can now say that okay, so instead of looking over S is in between 0 and tau, I look at what is where, like, for every, because this x tau is bounded within minus a half to a half. So I can instead take the supremum over the x bounded by 1 minus a half to half. And so the term that I'm left with is just this sum of the absolute values of the second derivatives where the i's and j's are not equal. And so this is like exactly equal to the sums of the, I use the other inequality that I talked about, which said that instead of looking at x, I can just look at 0. So I can take it out of the supremum, and then this sum of I not equals to j of like partial I j f. Oh, okay. Sorry. So if the I is not equal to the j, then the partial ij of f is just exactly equal to like the coefficient associated with f at I and j. So this is the one where I wrote f is equal to this sum of this function of c sub s x sub s. It's a subset of n. Okay, and then after I put all of those things together, I will eventually get like the term that I want. So actually, like, all of these steps are really just sort of, you just do the obvious bound after I have all the lemmas put together.
The last inequality is at the norm of the Dirichlet kernel. Why is it log n?
Oh wait,
I mean polylog.
Oh,
Yeah.
so this thing is like that theorem that I talked about, and like also another recent paper that said that if your function is, if like f is low degree, low depth circuit, then the second order like coefficients of the polynomial are going to be low. So I guess this is like just, yeah, it's like a property of why f is like easy to compute. I guess like sort of a priori it could be like all the second level coefficients could be something like square root n, but instead, because it's like because it's a very restricted class, it has to be polylog.
Okay.
Yeah, and so I guess this is like yeah. So okay, I guess I'll remark that, like, I guess in the sort of original proof by Raz and Tal, they sort of also had this idea using Gaussians, but they didn't sort of have this like formulation using the stochastic calculus part. And I think it makes it slightly easier when you just like, apply Dynkin's lemma, and like you can see where the bounds come from. So yeah, okay. I think I'm basically more or less done. So I think I'm just gonna talk about, I guess, like here, what the main takeaway from me is that instead of thinking about these bits as like being generated from ±1, first I have this thing where I think of the distribution as being over -1, 1 to the n, and then I do this other step where instead of saying that it's just a distribution, it's like a distribution generated by a stochastic process, and then I round the stochastic process back to the original ±1. So yeah, like I guess what this got me is just I could use like Dynkin's formula, and like just it's sort of everything fitted together very nicely. Right, so I guess there's like some other stuff. So okay, in this proof, I only use like the second order derivatives, but you can sort of induct on this proof and extend it to some higher level derivatives, and that like gives some other implications in the like quantum complexity world. It says some other more complex, maybe more like it just says some other, it gives some other separations between other like complexity classes. And so it solves some like variants of the Forrelation problem. And I guess there's also a new, like some of the newer results also use like variants of this kinds of idea in the proof, like using Gaussian interpolation and stuff like that to solve these problems. So yeah, I guess that's all I have. I hope this was cool.
Thanks. Yeah, it was really cool. So thanks very much. I'll clap myself, and I'll encourage other people to as well. And I'll stop.